Hi, welcome to your Mac 200 Statics online classes. Today we're going to finish the content of Chapter 2. This is the last video of this chapter and we're going to review the mathematics used to perform calculations with vectors. I hope you enjoyed this lecture. In this section, we'll introduce the concept of position vector. We are going to see that this vector is very important for the formulation of a Cartesian force vector directed between 2 points in the space. We start with the location of points in the space through a x, y, and z Cartesian coordinate system, like this. We'll keep using the right-handed coordinate system to do it. Then, let's consider that we have a point A, located somewhere here in the space. Taking the coordinate system as a reference frame, we can easily describe the position of this point by taking its coordinates relative to the origin along the x, y, and z axis. Those coordinates are simply measurements of the position of the point A from the origin. And for this numerical example, we store this information as 4 meters in the positive direction of the x-axis, 2 meters in the positive direction of the y-axis, and 6 meters in the negative direction of the z-axis. Now, let's consider another point B, located at this position right here. We do the same thing we did for point A. Take the coordinates along the x, y, and z axis and store this information as 6 meters along the positive x-axis, 1 meter along the negative y-axis, and 4 meters along the positive z-axis. With this information, we are ready to define the position vector r using the Cartesian notation for the points A and B. For the point A, we have the vector r sub A, denoting the position of the point A from the origin of the coordinate system, written as a Cartesian vector using its coordinates. And for the point B, we have another position vector r sub B, denoting the position of the point B from the origin, also written as a Cartesian vector using its coordinates. We can go further in this analysis and define a distance vector r sub AB, denoting the distance between the points A and B, or simply the position of the point B relative to the point A. This is mathematically represented by the subtraction of r sub A from r sub B. Expanding this formula using the Cartesian notation, we get the general expression to calculate the distance vector between 2 points, which is a function of the coordinate system of the 2 points along the axis of the reference system. Now let's look at one example of how to determine the vector position in a simple problem. In example 2.10, we are asked to determine the length and the orientation direction of the elastic rubber band shown here, attached to the points A and B. We can see in the sketch that the coordinates of the points A and B are given, which makes the solution very easy to achieve using the concept of vector position and vector distance. First, we need to get the position of each point from the coordinates given in the problem. For point A, we have 1 meter along the positive x-axis, 0 meters along the y-axis, and 3 meters along the negative z-axis. For the point B, we have 2 meters along the negative x-axis, 2 meters along the positive y-axis, and 3 meters along the positive z-axis. Then, by using the general formula provided in slide number 2, we can calculate the distance vector between the points A and B, which has this form in the Cartesian notation. Finally, we can calculate the length of the rubber band simply by taking the magnitude of the distance vector, given by the square root of the sum of the magnitudes of its x, y, and z components, which gives us the final answer of 7 meters. To answer the second part of the question, we're going to use the direction angles of the distance vector, alpha, beta, and gamma. Do you remember the cosine formulas presented in the last video to calculate the direction angles? We're going to get the arc cosine of those formulas using the magnitudes of the distance vector and its components to obtain each one of the direction angles. Let's talk now about a common situation in 3D statics problems, in which the direction of a force is specified by 2 points through which its line of action passes. This situation is shown in this figure right here, in which the force F acting along the rope can be represented as a Cartesian vector by establishing first a position vector r along the length of the rope from the point A to the point B. This situation can be further explained in this other figure, in which the x, y, and z Cartesian axes are established along with the unit vector u that defines the direction of both the rope and the line of action of the force. Then, the Cartesian vector notation of F is defined as the product between the force magnitude and the unit vector u, which is written in terms of the Cartesian notation of the position vector and its magnitude. Now, let's recap the important points regarding the concept of position vector and its applications. The first point is that a position vector locates one point in space relative to another point. The second point is that the easiest way to formulate the components of position vector is to determine the distance and directions that must be traveled along the x, y, and z directions, going from the tail to the head of the vector. And the last important point is that a force acting in the direction of a position vector can be represented in the Cartesian form if its unit vector is known, and then the force vector can be determined using this formula. Now we are ready to start working on some examples. In example 2.11, we have a man who is trying to pull on a cord with a force of 70 pounds. Then we are asked to represent this force acting on the support A as a Cartesian vector and determine its direction. This is the typical problem that gets easier to solve when we represent the length of the cord as a distance vector r extending from the point A to the point B, which is aligned with the force F. It's also convenient here to include the unit vector u aligned with both F and r. The first thing we have to do is to determine the distance vector. In order to do that, instead of subtracting the coordinates of B from A, we can get the distance vector directly by taking the distance to travel from A to B, which are 24 feet towards the negative direction of the z-axis, which in the vector form is minus 24k, 8 feet towards the negative direction of the y-axis, which in the vector form is minus 8j, and 12 feet towards the positive direction of the x-axis, which in the vector form is 12i. Then, joining these pieces together, this is the result for the Cartesian representation of the position vector. Also, we can get the magnitude of the position vector by simply taking the square root of its components, which results in 28 feet. Now we have everything we need to obtain the unit vector u, which is determined by dividing each component of the vector r by its magnitude that we just calculated, and this is the result. Now that we got the unit vector u, we can use it with the magnitude of the force F, which is 70 pounds, and apply the formula in slide number 6 to get the final answer for the Cartesian vector notation of the force F. For the second part of the question, we have to determine the direction angles of F. To do it, we can see that it's much easier to calculate these direction angles if we establish a new coordinate system, x prime, y prime, and z prime, with its origin in the point A, rather than considering the original coordinate system, because the angles alpha, beta, and gamma are readily visible in this new coordinate system. With this information, we calculate the three angles using the formula presented in the last video, taking the arc cosine of each component of the unit vector u, and we get the final answers for the second part of the problem. Now it's your time to study examples 2.11 and 2.12. Carefully review the procedure given in this video and make sure that you fully understand all steps you should take to solve those problems. A very common problem in statics is how we can find the angle between two force components, assuming that we fully know their respective magnitudes and directions. This can be easily solved by considering the dot product between them, which is represented by this formula, where the angles between the two vectors must be between 0 and 180 degrees. Since this operation is very similar to the multiplication between two vectors, which results in a scalar number, the same laws of multiplication operations, such as the commutative, multiplication by scalar, and distributive laws, are valid for this case. We can also establish a general expression to calculate the dot product between two vectors when we have their Cartesian vector notation, in which we simply multiply their corresponding x, y, and z components and sum these products algebraically. Now, we are going to talk about two different practical applications of the dot product. As we talked earlier, we can use the dot product to determine the angle between two vectors. And from this general expression, the angle can be directly calculated from this arc cosine function here. Another application is to calculate the components of the vector parallel and perpendicular to a line. Let's take this example here, in which we have to find the components of the force F acting in the direction of the beam and the other component perpendicular to that beam. For the component of F parallel to the beam, FB, we can define a unit vector UB aligned with the beam and the angle theta between F and FB, which can be defined using the cosine of theta, or the dot product between the force vector and unit vector. Additionally, if we want to determine the perpendicular component of F, then we can take either the sine of theta or the Pythagorean theorem with the magnitudes of the two other force vectors. Before we go to the examples, let's highlight the most important points of the dot product between two vectors. The dot product can be used to determine the angle between two vectors or the projection of a vector in a specified direction. Also, if two vectors A and B are expressed in the Cartesian form, the dot product is determined by multiplying their respective x, y, and z scalar components and algebraically adding the results using the formula shown here. Next, from the definition of the dot product, the angle formed between the tails of vectors A and B are given by the calculation of this arc cosine formula. And finally, the magnitude of the projection of the vector A along a line AA, which has its direction specified by the unit vector UA, is determined from this dot product expression. Now let's see one example of the application of the dot product to solve statics problems. In example 2.14, the goal is to calculate the magnitude of the projections of the force F, as shown in this figure, in the u and v axis. I want to call your attention first for the fact that in this case, we are talking about the orthogonal projections of the vector F along this axis, in which the angle formed between the lines drawn from the tip of the vector must form a 90 degrees angles with the u and v axis. To solve this question, we can apply the dot product separately between the force F and the unit vector u sub v parallel to the v-axis and u sub u parallel to the u-axis, which can be reduced to the trigonometric relationships involving the cosine of the angles 45 and 15 degrees. And this gives us the result of 70.7 newtons for the u projection of the force F and 96.6 newtons for the v projection of the force F. And with that, we have finished chapter 2. Thanks for watching, and I'll see you in the next video.